It's now time to move on to Chapter 5, Section 1, where we're going to start talking about groups of numbers. So specifically, we're going to look at the factors of natural numbers, identifying prime and composite numbers, finding the prime factorization, finding the greatest common factor, and finding the least common multiple. So natural numbers are what we call counting numbers. They're numbers we can count on our fingers. So 0, being 0 fingers, technically is not actually a natural number. So it's numbers starting with 1. And they have to be whole because I can't count 1.5 on my fingers. Every natural number can be written as the product of 2 or more numbers. For example, 12 can be written as 3 times 4, 4 times 3, 6 times 2, 2 times 6, or 12 times 1. So there's lots of different ways to get to these numbers. The natural numbers that are multiplied together are called factors. So if I'm looking at 12, for example, the factors of 12 include 3 and 4. Now they would also include 2 and 6 and 12 and 1, but you know what I'm saying, it's the beginning piece. So if I wanted to list all factors, I would have to come up with all the combinations of numbers that I can multiply to get 12. Now it's important to note that when I do that process, I don't write numbers twice. So even though 2 times 6 is 12 and 6 times 2 is 12, I only record that one time. So here's an example of finding those key factors. So if I want to find all the factors of 24, this is an exercise in a list. So there's no way to do this. There's no mathematical formula other than to sit down and list them all out. So I have the list right here, here at the bottom, 1 times 24, 2 times 12. So I've listed out all the combinations of things I can multiply together to get to 24. And then I'm going to put them all in a list format because when we tell them factors, they are in list format. It's very important you put a space behind the comma in Alex, or it tries to read as 1, 2 is its own number, not 1, 2. 2 is an easy example of a number that only has 2 factors, 1 and 2. 1 times 2 is 2. I have no other examples, no other factors that multiply to give me 2. You could also think of 7, 5. There are quite a few prime numbers that only have 2 factors. And then in part C, is there a way that I could write 24 as a factor of 3 numbers? So what I did to do that was, if I know 4 times 6 is 24, and I make 4 into 2 times 2, that generates 3 factors being multiplied together that gives me that 24. For divisibility, I'm going to use the ideas of factors and I'm going to build upon it. So a natural number is divisible by another if dividing A by that factor B results in a remainder of 0. So if it is a factor, when I do the division, I should have no decimals, no remainders. So for example, if 6 is a factor of 24, then 24 divided by 6 is 4 with no remainder, so it checks out. However, 5 is not a factor because to do 24 divided by 5, it's 4, remainder 4. So because there's a remainder, it cannot be a factor. So for this reason, we will sometimes say that factors are divisors. And so when I say divisors, it means they just divide evenly into that number. Prime numbers are numbers that have 2 factors, 1 and itself. Therefore, 1 is not a prime number because you need 2 factors. So 1 and 1 is the same number, which is why 1 is not prime. If you have more than 1 factor, then we call it a composite number. So if I look at 25, I know that 25 can be found by 5 times 5, so it's composite. I know the only factors of 17 are 1 and 17, so it's prime. In 12, it's composite because we just showed at the beginning of this lecture all kinds of ways to get to 12. And there are no factors of 31 other than 1 and 31, so that is also going to be prime. Now, the fundamental theorem of arithmetic is helpful. Every composite number could be written as a product of prime numbers, meaning I'm going to break every factor down into the smallest component. So I know that 12 is 2 times 6, but I could write 6 as 2 times 3, which is why I can write the factors out as 2 times 2 times 3. On the other hand, I could also say 12 is 3 times 4, and 4 is 2 times 2, so I'm replacing the 4 with its factors to get a list of prime numbers that are multiplied together. So we call that the prime factorization. So if I look at this example, find the prime factorization of 100. Now, when they say the tree method, that is just good old dig into it and figure out the factors. So if I look at the halfway point, 2 times 50 is going to be a prime factor. 2 cannot be broken down any further, but 50 can. 50 can be written as 5 times 10, and then 5 cannot be broken down any further, so it's 5, but 10 is the same as 2 times 5. And then I have a 5 remaining. So that's how I'm generating this factor tree, so that I get 2 times 2 times 5 times 5, or 2 squared plus 5 squared. Those are 2 different ways to write the answer. That way is a little frustrating at times because you just have to sit there and think it out. If you're doing the division method, then first you're always going to start with the middle by dividing by 2. Once I divide by 2, I'm able to see that that is 70. So then I'm able to say, okay, now I'm going to break 70 down and divide that by 2, and that's going to be 35. And then I know 35 is divisible by 5, which is a prime number, and it goes into it 7 times. So I have all prime numbers here that I followed up the ladder, which is why my prime factorization is the given number. So the division method's always going to start by dividing the number by 2. And basically, once you get it down to something that's small enough, like 50 or below, then you're able to actually go into factors that are prime. The greatest common factor of 2 or more numbers is the largest number that both of those are divisible by. So the only way to find this is to list the factors. So I listed the factors of 18 and I listed the factors of 24. If I look at the numbers, I see the highest number that's present in both sets is 6. So 6 is the greatest common factor. So if I want to find the greatest common factor for 2 or more numbers, I just have to write out the factorization. There's no simpler way to do this. It's just a list of processes. Then I'm going to map them, so I write them over on top of each other, just like we did here. And then I'm going to find the 2 numbers. So if I look at this example, find the greatest common factor of 72 and 180. I'm going to actually list the prime factorization out for 72 and for 180. And I'm going to map them onto each other. So 2 and 3, but 3 is also in common. And so I get 2 to the third times 3 squared. Here, I also get 2 to the second times 3 squared. So then my greatest common factor would be 2 squared times 3 squared, which is 36. Or if you just wanted to do this with factorization and not prime factorization, you could just list all the factors out. If I want to find the greatest common factor of 3 numbers, I'm going to factor all 3 numbers out. I'm going to list the common factors. So I have 2 squared in common in each one, because if I have 2 cubed, I have 2 squared. So that's a subcategory. I also have a 5 in common. So I'm going to do 2 squared coming from, they all have 2 squared in common. And then 5, because they all have a 5. They don't all have a 5 squared, but they all have a 5. and that tells me the greatest common factor is 20. So how do we apply this to a word problem? So take a minute and pause the video so you can process the word problem, and then press play when you're ready to rejoin the problem. So the number of packets per box has to be a factor of 200 and 280. That way I don't have any left over. I don't have a remainder. So if the boxes are supposed to contain the largest number of packets possible, then we need to find the greatest common factor. So I'm going to do the prime factorization of those numbers. They each have a 2 cubed in common. They each have a 5 in common. So my greatest common factor is going to be 2 cubed times 5, which is 40. And so that tells us he should put 40 packets into each box. Now the least common multiple is the smallest number that they have in common, which is a little bit easier, right? So if I want to find the least common multiple for the numbers 18 and 24, I would want to write the first 5 multiples of each number. So I've got the first 5 here. So I'm counting by 18s, I'm counting by 24s. The first number on the list they have in common is 72. So that is the least common multiple. If I want to write the prime factorization, then I would do the prime factorization just following the normal process. Now they wanted me to also do the prime factorization of the least common multiple. And what's interesting, as you can see, they're all made with 2s and 3s. So if I wanted to get a procedure together to list how to find the multiples of 2 or more numbers, we can write out the prime factorization. We can make a list of every prime factor that appears. And then we can choose the largest that appears in a factorization. And the least common multiple is the product that you listed. If that sounded like gibberish to you, list the multiples out until you find one they have in common. You don't have to use the factorization method if you understand the multiples method. So here's an example. I have 3 numbers, 24, 30, and 42. I'm going to do the prime factorization for each. So this is the prime factorization for 30, the prime factorization for 42, and 24. List all the factors that appear together. So I have 2, I have 3, 5, and 7. Because the largest exponent is 3 of 2, I use that value, and then I use 3, 5, and 7, and that gets me to 840, which would have been a very difficult number to get to from the multiple list.